Welcome. I'm Volker, and together with Osama, we're representing the Autonomous Vehicle Computing Consortium. And in our talk, we are talking about the definition of a system architecture of autonomous vehicles. So let me give you a brief introduction to the AVCC. So what is the AVCC? As I said, it stands for Autonomous Vehicle Computing Consortium, and it is a group of automotive and technology industry players who have come together to collaborate and work on a common compute architecture. This architecture is intended to build consensus across the industry on automated and assisted driving solutions, with a particular focus on autonomous vehicle compute. If we look at our members, our membership comes from all across the industry. So we have OEMs being members at the AVCC, traditional tier one suppliers. We also have technology companies, especially from the semiconductor industry. We have mobility service companies and commercial transportation companies joining in. But besides that, we also have members coming from research and higher education institutions. And also the AVCC is building collaborations with existing industry organizations and groups. So looking at the conceptual system architecture, it's considered to be a foundational document of the AVCC and its activities. Its main purpose is to create a common language and a reference to all the activities at the AVCC so that we know where we are and what we have to focus on. This system architecture is intended to represent all levels of automated driving according to SAE international definitions. And it's supposed to break down the problem of an autonomous driving solution into sub-blocks so that we can focus on individual blocks. The architecture is represented in two principal views. The first one is a functional view, and the second one is an informational view. So if we look at the first one, which is on the next slide, it's the functional view. It's basically a block diagram in which every block represents one function of an autonomous driving solution. We have on the left-hand side in the blue boxes the functions which we consider to be essential to autonomous driving, and they are also kind of typical for autonomous driving. Then we have a second category in the boxes which have this kind of lavender color. These functions provide data which are used for solving the autonomous driving problem, but they are not specific to autonomous driving. It's usually data that is anyway available in the vehicle, but it's also consumed by core ADS functions. And then on the right-hand side, we have the green boxes, which kind of represent infrastructure functions and features which aren't necessarily needed to build an autonomous driving solution. For example, security. You don't need security to drive autonomously, but you need all of them to build a proper system that you can deploy into the field in a car. So you need to secure your autonomous driving car against hacker attacks, and that's what you need security for. In fact, some of these items the AVCC considers so important that it has established a dedicated working group, for example, to work on cybersecurity topics. So looking at the information flow visualization of our system architecture, we focus on the blue boxes, which we consider the core functions of an autonomous driving system. And we decided to also discuss what information is exchanged between the functional blocks, because if we do not pay attention to the information when developing an autonomous driving solution, we can easily make bad choices and create bottlenecks when it comes to information exchange between these functions. And therefore, we also believe that it is necessary to create an overview to guide us through discussing the development of autonomous driving solutions with regard to the information flow. Now, if we zoom in to this graph, I mean, it's a bit small, so I have 4 slides which go from the left top corner in clockwise orientation through this graph to zoom in a bit, and I will give more details on that. So if we start in the top left corner, you can see to the left side of this view a little dotted line box which says environment sensors zoom in. So this is basically where we get data from the sensors like cameras, radars, and lidars into the perception block, which is one of the functions. It does some computation and it generates signals, which it then forwards to subsequent functional blocks. If we look at the top right corner, we again have a sensor input, something about left top, again, a dotted line box. But you also recognize the lavender color boxes, HMI and connected services, which represent these needed but non-core functions for an ADS solution. And they again provide data for the functions to make the computations with, but also sometimes intermediate data are forwarded to these blocks, for example, to the HMI for visualization for the passenger of the autonomous driving car. Again, the blue boxes and the main functions do computations, produce intermediate results, and forward them to subsequent functional blocks. So if we look at the bottom right corner of the information flow view of the system architecture, we can see functions like behavioral planning, trajectory planning, and motion control. And as mentioned previously, they are exchanging intermediate results between each other. So in the whole visualization of the system architecture, there is a notion of stepwise processing of data and intermediate results. And this also implies something like a quantized time. Now, we need to stay on a generic level here and cannot make this very specific, because in the end, this is also supposed to guide our member companies when developing their solutions for ADS systems. And therefore, they all will be a bit different, and the AVCC could not make an ultimate decision what the timing and the time frames would be. But keep this in mind if you dig deeper into this visualization. There is a notion of stepwise processing and also of quantized time. And finally, looking at the left bottom corner of the information flow visualization, I mentioned it already, we have motion control, and this is important in a way because it's interfacing to actuators in the vehicle. So after all, the driving decisions and maneuver planning, ultimately a request has to be placed, for example, to a brake or to an engine to accelerate or to decelerate. And this is very much in the middle at the bottom of this slide, where we say this is where a request goes out to an actuator. Now, I followed through this information flow in a clockwise manner, but also we have some information going just across all these functions. And this is detailed on the next slide. There is a signal highlighted in red, which is called regions of interest. And it goes from behavioral planning. So I have this little zoom in on that behavioral planning, which produces this signal, and it is consumed. There's another zoom in by perception, which consumes regions of interest. And this, to stick with the signal as an example, regions of interest is supposed to represent, after we plan a maneuver, we know where we are going and we know where to focus the attention of the system. So we don't have to analyze the whole input of our cameras at the same level of detail. And this information where we need to look at is communicated to the perception block, which then can focus processing and accuracy maybe on that specific region. And this is serving as a simple example of something that I would call a feedback loop within this system architecture and this information flow that we are processing. So on the next slide, addressing complexity, I want to discuss a little bit the fact that we intended this system architecture to be applicable to all levels that SAE International has defined for automated driving. The main idea that we have is that all of these functional blocks are maintained. They are in every version, in every scalability or scaling version of an autonomous driving system. The difference is that these functions change with regards to the complexity of their function implementations. And we could see an extreme where functions in a very low-level system would be scaled down to a state where they would become trivial, meaning just forwarding data, or in a mid-range scaling scenario, they would be simplified but still do some considerable computation. And then other functions would remain as is. And the composition of these different scalings of functions implementations would then be able to represent all different levels according to SAE. With the next slide, we are looking at scaling performances. So when we talked about the system architecture, we also at one point wanted to match these functions to underlying hardware. But we found this to be very difficult, not just because of the intent of members of the consortium to differentiate in their solutions, but also there isn't that the precise solution to build such a system. So the best that we could do is describe some sample points, which would be examples of systems. It's not a specific configuration that is mandatory. It's just supposed to give some orientation. And these sample points differentiate in the sensor setups, the sensor suite. For example, the number of cameras, the number of radar sensors, ultrasonic sensors, and so on. There can also be different resolutions in cameras, which would differentiate these levels of systems. And for each of these sample points, we also try to give example, high-level, vehicle-level examples of the functions that could be implemented on something like that. Now, again, we wanted to map this to the functions as in the system architecture block diagrams. So we also talked about what hardware, what compute elements would be able to host such functions. And in many cases, we said this could be done with something based on machine learning. And while still trying to map this also to performance numbers, we realized when we start talking about machine learning and talking about performance, that the available metrics aren't really convincing and don't really appear to be a good tool to talk about this. And that's a point where the AVCC decided to set up a benchmarking working group, which is chaired by Osama, and Osama will share details on the working group's activities in his part of the presentation.
Thank you, Volker. My name is Osama Nirouk. I'm chair of the Micro Benchmarks work group at AVCC. Let me start by laying out the case for why we need automotive compute benchmarks. As you probably know, demand for silicon and for compute in the automotive domain has been rapidly increasing. In fact, recently we've seen some OEMs have to shut down their production lines due to silicon shortage. Which leads to the question, what is the silicon doing? And even beyond automated driving, there are a lot of safety features that are enabled by software running on advanced SoCs. So we see both automated driving as well as safety features as drivers for the demand for the silicon. So far, the automotive industry has not come up with a consistent language or a consistent benchmarking approach for measuring the performance characteristics of these automotive SoCs. This is a gap that we at AVCC feel we are uniquely qualified to address due to our membership. And so what we've set out to do is come up with a set of recommendations specifically targeted at automotive compute benchmarks. On slide 15, what are the challenges with trying to work on automotive compute benchmarks? The first and perhaps the biggest challenge in comparison to regular computing is that in the automotive domain, our hardware is concurrently running numerous functions all at the same time. So we would have the image signal processor processing incoming data from cameras. We would have deep learning accelerators, general purpose compute engines, real-time compute engines, and in practice, several other engines all running at the same time. So far, our approach to characterizing performance has been somewhat antiquated. So in our conversations day-to-day, dry stone MIPS, or millions of instructions per second, and tera operations per second in the deep learning domain are quite common. But as we know, they're not representative of real-life systems. And from history, we can learn that focusing on the wrong metrics can lead to negative outcomes. And I cite an example of TOPS, or tera operations per second, in deep learning. If you look at publicly announced SoCs from the past decade or so, we've gone from 0 to SoCs that are announced for automotive domain over 1,000 TOPS. The challenge with that is that it ignored things like power efficiency, thermal dissipation, and many other challenges that have to be addressed in addition to pure performance. The way AVCC has approached benchmarking at the automotive level is with two different perspectives. One is a top-down perspective, and one is a bottom-up perspective. So the top-down perspective was the system-level benchmarking approach. Based on what I said a little while ago, we typically want to see many workloads running in parallel. That, however, requires us to have a software framework for composition of such benchmarks from component benchmarks. So we put that work on hold for a moment, and we switched to what we call micro benchmarks. Micro benchmarks consist of individual workloads that we get from the systems workgroup that Volker described earlier. So looking at that systems functional blocks diagram, we see that there are different types of workloads covering general compute, deep learning, vector operations, and so on. And so these are what we call micro benchmarks. We use them to focus on specific workloads, and later on we can compose these into system-level benchmarks. In the remainder of this presentation, I will focus on micro benchmarks. The way we've been approaching micro benchmarks, as I said, is we're starting out with the system architecture. We are starting out with these different workloads and the types of algorithms that are embedded in each of those diagrams. We are looking for the state of the art and trying to build on that state of the art in benchmarking to adapt it to automotive. And I will walk you through an example in a moment. Along the way, we're also generating the proper terminology to help us talk about the characteristics and the quantifiable metrics that we need to continue this innovation in automotive electronics. One example that we are working on right now of this micro benchmarks is machine learning. So again, the entirety of machine learning for us, we consider to be a micro benchmark because it's running in parallel with numerous other systems at the same time. This is an area where we've seen very rapid rise. Historically, cameras were using classical computer vision algorithms, but lately we've seen that detection and other tasks are best done by machine learning approaches. And so this domain has taken over how we do machine vision in automotive contexts. The state of the art in machine learning benchmarking is a suite of benchmarks called MLPerf, which is owned and maintained by ML Commons organization. And ML Commons have done a great job creating a suite of benchmarks that address everything from high performance computing to servers, mobile, phones, etc. However, they don't have any coverage for automotive. And this is where our work group has been focused on trying to take that benchmark and turn it into something that works best for automotive. Our approach for that is by analyzing in great detail what they've done, decomposing it into components, and then adapting those components to automotive. So if we focus on inference, which is the typical operation we would expect to see done in cars, and we take the inference benchmark from MLPerf, we can break it down into the following components. So there are the actual models that are running the inference. We have the data sets which we use to train those models or CNN models and also to evaluate results. We have the evaluation scenarios, things like whether I'm processing one frame at a time or processing multiple frames at the same time. There are different metrics, both performance and power, that you have to measure. There's an automation harness as part of MLPerf, which ensures that everyone is running the benchmark in a consistent and reproducible way. And finally, there's a set of rules that you have to abide by in order for your results to be valid under the MLPerf benchmark suite. So for each one of these axes, we were able to take them and find what do we want to do in the automotive domain. We tend to have different models that we'd like to use. The automotive domain is rich. When it comes to data sets, we have a lot of different data sets from different vendors covering different cameras. LiDAR, radar is also becoming common, and so on. So what are the expected benefits of the work we are doing in the micro benchmarks work group? Well, first and foremost, by defining these measurable characteristics of the future architectures, the future hardware and SoCs, we enable tier ones and OEMs to continue this innovation path they've been on, and we enable IP vendors and SoC vendors to also rise up to that, to those requirements and focus on the appropriate features which are quantifiable in a way that we all agree on. We think that's very important for the industry. Second, in the automotive supply chain, we typically refer to what we call requests for information and requests for quotes, which are different ways of exchanging information about our parts. Today, those are done in a very inconsistent way when we compare different vendors. We would like to have a far more consistent approach to these technical parameters that enables tier ones and OEMs to do a quick apples to apples comparison. And finally, we get away from the antiquated metrics that we mentioned earlier, like TOPS and DMIPS, and we focus on more appropriate metrics that are reflective of real-time system performance. Our current report, Working Text 3, is entitled Conditions and Metrics for Automotive Deep Learning Benchmarks. We plan to publish it in Q4 of 2021. And as I hinted a little while ago, we have already collected data from our members on what are the models and data sets that make the most sense for automotive domain, what are the scenarios we hope to look at, again, looking at the different sensor suites, and all of that is work we hope to publish next year. With that, I will hand it back to Volker. Thank you.
Thanks, Osama. If you found our presentation interesting, there's more content available. The AVCC you can find on the internet at avcc.org. We have published 2 technical reports so far. The first one is on the conceptual architecture for automated and assisted driving systems. And there's a second technical report focusing on the image signal processing, which is just in front of the perception functional block. Osama is working also on a technical report. It's not published yet. It's work in progress, but it's coming soon. And in our day jobs, I'm Volker Hampel, working at Continental. Osama Neyrouk is working at Renesas. And if you have further questions, you can contact us by email. And thank you very much
for your attention.
And for attending this session.
And we hope to see you soon.